Okay, well, let's list again. Let's reproduce our results again and list again what these graphs are. Okay, so what we had here, this should be our full story down here. Actually, it may not be our full story. Okay, let's reproduce these definitions again. Okay, so let's remember, okay, so let's list our types of graphs for a minute. Okay, so first of all, we had the spatial reconstruction up here, right?
Right, which, let's see, what is it exactly?
Well, let's read through what we've got here, okay?
So this is events at vertices and...
Right. Okay, so this
is... What are edges exactly?
This one is basic spatial hypergraph. And what this is...
Also known as atoms expressions graph. It is atoms at vertices expressions.
Well, elements relations graph. Elements relations, aka atoms expressions.
Yeah.
Okay. Okay, that's that case. All right, next case is
so what do we call this concept where nodes are connected by having shared ancestors in the
well, that's what we have. That's what we have called the branchial graph, but this is the spatial analog of the branchial graph.
Yeah.
Or the causal analog of the branchial graph, actually. It's the causal / spatial analog of the branchial graph.
Yes, it events common history graph, essentially.
Yes.
Whereas branchial graph is states common history graph.
Right. Well, this particular one here is events common history. This graph is events common history.
Yeah, so there are three things about graphs. What's at vertices and edges, and which vertices are selected. In this case, another feature of it is that vertices are selected at a particular step.
Right. Well, okay. So look. The elements of, well, the components of a hypergraph. Okay, and there are basically two. Okay, so what are the components of a hypergraph? There's basically there's the nodes, the vertices, and the edges.
Yeah, so type of vertices, type of edges, and then selection of vertices. Because, for example, causal graph is a, well, it's events causal graph at the entire history.
Well, hold on.
Well, okay. For causal graph, doesn't make sense, but
okay, hold on. Types of vertices. There are two. Well, okay, there are the elements, aka atoms.
Yeah, the expressions.
There are relations, aka expressions.
Events.
And there are events.
There are also states. I mean, not.
Well, then there are whole states.
Yeah, not in set replace, but generally.
Yeah, then there can be
states.
whole states. Okay.
Is it really all? I mean, there might be combinations of those as well.
Yeah.
Like an
okay.
expression events graph.
Right. Yeah, you can have multiple types of vertices in a single graph. Right. Okay,
Yeah,
so
but I guess that is all, yeah.
Types of edges. Okay, so one type of edges is relations. I mean, basically the same thing again. Relations can be an edge. Events
right, the same thing plus.
hold on. Plus elements can be an edge, i.e., what relations contain the same elements. And this is, i.e., what elements are in the same relation, right?
Well, it depends on what set of vertices, because if you have events relations graph, which is, events relations graph is a causal graph.
Okay, hold on. So you're saying
relations just mean you connect vertices, whatever they are, by the fact that they're related to the same expressions.
Okay, so hold on. So the types of edges. So is there a case where the edges are events?
Well, of course, states graph.
Oh yeah, right.
Well, we don't have expressions events graph, but we definitely could. And it would just be another way to compress expressions, events, causal graph. I mean, we have expression, events, causal graph, which has two types of vertices. It can be compressed into a causal graph, also known as events causal graph, but we can also compress it into expressions causal graph.
Okay, there's an additional type of edge, which is a common history edge.
Yeah.
Right?
And there's also causal edge, which is not the same. Common history, common future.
Which is otherwise known as will lead to the same event, right?
Yes.
Okay, now what is a causal edge?
Well, it means there's two vertices are one in the past and one in the future. Well, one causes the other one.
Yeah, but what is that in terms of these kinds of things? That means that there's an event.
Ordinary causal graph is an events causal graph. It has edges, which are essentially causal relations. I mean, you could think of them
this means is common. Look, what this is common components. This is saying common components in objects, right? It connects objects with common components. Connects objects
by components.
Well, which share components, right? So they can share
what components?
Relations. Well, whatever, because this could connect objects which share components, for example, that share elements.
No, because basic spatial hypergraph, for example, connects atoms if they share components, so that is expressions, but it's not a causal graph in any sense.
Okay, well, okay, connects.
No, causal just means one causes the other one.
Right, I understand. Connects objects where
Time like separated. Well, no,
that's
not
basically
quite.
time like separated, yeah.
It directly causes, not because otherwise you would get
Right. Connects objects which directly cause each other.
Yeah.
And share components by virtue of sharing components.
Well, sure. If they cause each other, they have to share components in some sense.
Right. Okay, so then what is the common history in the same terms?
Well, there is an object which is caused which is caused or did cause both of them.
Right. An object causes both. One object causes both items. Let's just do the common history case. Causes both objects. Okay. So one object causes both objects, and this is one object causes another object.
Yeah. There are basically 20 different graph types.
No, there aren't. There's more than that because you can have combined things with it's worse than that.
Maybe we need to have a function which would automatically figure out how to make that graph.
Yes, that's possible. Given the components, we could certainly make that. Okay. So, and we also need to say what color each of these things is, and so on.
Yeah.
Okay, so these types of edges, you can have, if it's this type of edge. Okay, so let's write out what types of graphs there are now. Okay.
So there are also selection of vertices.
What does that mean?
Well, you when you make a graph, you select vertices from out of all that are possible.
Oh, I see. Well, and also edges probably. Selection of objects to put in the graph.
Yeah.
E.g., so that could be by foliation, e.g. by foliation.
Well, you either only select, well, two obvious cases is when you only select space like separated ones by specifying the foliation, or you select all of them, like in a causal graph.
Well, okay, so one thing is, okay, so one of them is anti-chains, right?
Yeah.
Selection of objects to put in the graph. Okay, so we're starting from a post set, right? So we can either select chains or anti-chains, among other obvious.
Well, it's space like separated only anti-chains, a branch like separate only pose.
Okay. E.g., space-like anti-chains, branch-like anti-chains, etc. Okay. All right. So let's go down here and try and fill some of these in. Okay.
Right.
The basic hypergraph has. Okay. So let's describe what it is. Okay. So this is vertices are the elements. right?
Right.
The edges are relations,
Right.
right? And the selection is
Space-like separated foliation. Well, space-like separated subset.
Subset of what? Of relations or of elements?
Of elements. Oh,
Right.
hold on. No, relations. Elements cannot, doesn't
Yeah,
make
I don't think
sense
they.
with
I don't
elements of
think,
space.
right.
Yeah, relations.
Right. Okay. That's that one. Okay. Basic. Okay. So let's fill in. The next one is basic causal graph. Okay. In this one, vertices are events, edges are causal. Causal.
Actually, there
between,
can be either causal expressions. That's equivalent in this case. Well, more or less equivalent.
Oh, wait a minute. What do you mean? Their
So
expressions.
events, if you put expressions at edges, what it means is that the same expression is created by one event and destroyed by the next event.
Right. Causal or relations.
And technically, in this case, it's relations. That's why you can have multiple edges in a causal graph. That's why you have multi-edges.
Okay. Okay. So it's
Yeah,
sort
so
of.
one could argue causal would imply it would be a simple graph of this.
Okay. All right. So basic causal graph is the edges are relations, i.e., they connect, i.e., events that share a relation are joined. Right?
Yeah.
But they're only joined one step down.
Well, how else would they be joined? I mean,
if this
relation is destroyed, then it's destroyed. It can be used again.
Well, but couldn't this one share a relation with one down here? And I guess not.
It can if it's not destroyed yet by that time. And you can see there is an edge going from the second layer to the fourth layer on the right-hand side.
Yeah. So let's label in this picture. Okay, here I want to label these pictures, okay? So how do I do that? Can I just say, I want to label both the edges and the nodes here. Okay, so I say vertex labels.
Well, you can't label the edges.
Why not?
Well, because there's no option for it. Well, it's not very useful here because you already know what the edges are once you know the vertices.
Okay, but if I just say graph edge labels.
It's not a graph.
What is it?
The graphics. It's a hypergraph.
Okay, so we need labels for edges, which in this case will be simply things like that edge will contain 716. It'll be trivial, right? Labels for edges, which.
Well, the names are not the hard part. The hard part is figuring where to place them. Because, well, it's not that hard, okay?
Well, okay.
Because they are not always binary.
No, I understand. So you just put them in the middle of the polygon.
Right. Well, it's complicated because polygon doesn't have to be convex. You don't want to put it in the center of mass. You have to put it inside.
Okay. Anyway, though, okay. Which
Okay,
in
I
this
had an issue for it as well.
most edges, which in this case are just the list of elements at the ends of the edge. Or is that what edges always are in all these graphs?
Yeah.
Is what is at each end.
Right.
Okay, so now if I say vertex
So it
labels,
follows the vertex labels.
yeah. Okay,
Do you
now
really use edge labels?
ever?
Yeah.
I don't know. Okay, so anyway, so here, those numbers are pretty meaningless, right? How do I see the actual, how do I see what those events actually were?
Means the contents.
Yeah, now if
Well,
I
you
could,
can get the well, there are two layers of content. So if you have, there's property called events list, which would give you the list index the same way.
okay,
But it would be in terms of expression indices. And if you want to turn expression indices into expression contents into the atoms as well, then you have to use all expressions property for that.
okay, fine. Let's just do it. Okay, so we understand what we're getting here. So let's assume that the thing that we are keeping as canonical is the numbering of the elements. Okay. See what I'm saying?
Okay.
Is that a 0 there?
Yes, it's initial atom.
Okay. Okay. All right. So let's just write something here that says are you writing it?
I'm making an issue for all these things. We add the value for vertex labels, which would show contents of events and so on in the causal graph.
Okay, hold on. Let's just write the code right now to do this, okay? So you're saying that, so what we want to do is we want to say labeled causal graph of WMO colon equals. Okay, so what are we doing here? We're getting out, explain what we're getting out. We're getting out explain it again?
So events list first.
Okay.
So that gives a rule index and then expression indices.
Okay. Okay. So then, okay, so then we have to put those as the labels. Are they in the order 1, 2, 3, 4, et cetera, et cetera, et cetera? Is that what these are? Okay.
Well,
so we have
that's
to do,
the order in this list. The numbers are expression indices.
these are expression indices.
Yes.
Oh, I see. So
So if
now
you
we
want
have
to turn them into atoms, you need to do another step.
what's that?
So it's all expressions property. And now you need to substitute indices in the previous result.
Okay, I get it. Okay, so here, let's ignore the rule. Okay, so we're going to ignore that. So now what we're going to say is last/at. So I'm going to say ignoring which rule is applied. Last/at
Well, we are
WMO.
adding ambiguity anyway, because the same different expressions might have the same contents.
Okay, well, whatever. Okay, so that's the events list, okay? So now this /dot. Now what we want to do is we want to say with is WMO of all expressions. Okay, now we want to say here, we want to map hash replace hash.
Well, why do you need replace?
No, it's just a part.
It's
right
just,
here.
yeah.
Okay. Hash. No, it's
EM part hash
at level -1.
Well, level 1 is also fine.
No, it isn't.
Because you'll extract lists one at a time. Maybe faster as well. And you can put list into part.
Yeah,
It's
you can,
list.
but that's not going to work because these are A goes to B. That's what this is being applied to, is A goes to B.
Oh, I see. Okay. Yeah, never mind.
Okay, so that's that. And then this becomes, this is now vertex list. So now we've got the causal graph. Actually, all we have to do is say, no, actually, all we have to do then, if I'm not mistaken, is say WMO of causal graph, comma, vertex labels, arrow this, because I think they're just in that order, right? Am I right?
Let's see. Yeah.
What is events list here? Is that the right thing?
It should. I don't know why it's
Oh, I see. I know, I'm a very stupid mistake. Okay, what did we do wrong? Vertex labels. Oh, it thinks it's a list. Never mind. We got to do it the other way. We got to do it the other way. Vertex labels goes to
Oh, we need a thread.
No, we don't. We don't need a thread. We need a thread of vertex
range
list.
events count.
Well, or vertex list of. Okay.
I don't have a causal graph here yet.
Okay.
WMO.
Okay, hold on. What is it called?
Events count.
It's actually more beautiful than I would have expected.
Well, except sometimes expressions might have differentiality, and then it would be inconsistent. It would be matrices in some cases and lists in other.
Yeah. Okay, so this shows that, you know what, I'm going to put in an input form here. How would I do that?
I think there's an option for graph to do it, but I don't remember what it was.
Vertex style.
No, it's not a style. It's format type, I think. Standard form. Maybe some standard form we want, but we needed to avoid doing matrices.
Well, that's okay. I mean,
transition form. It's very long now because it's monospaced.
Is there any other information than format type in there, or where? Look, it's not difficult here. It's not difficult. This is thread range of this. How do we get it onto? Okay, here, what we want to say is, I think if we say here text slash at that, do the right thing. Crazy, crazy. Huh.
I had the same problem expression events graph, and I just ended up leaving them as strings. Well, I guess for labels it's fine because they're not supposed to be machine readable.
Oh gosh, that string has a dash greater than in it. Well, anyway, we can figure this out separately. All right. So that's what's there. So every event, you know, there is a label on this edge that is meaningful, right?
Expression.
It's the expression. It's what's shared between the two things.
Yes, I agree in this case, but it's also a lot easier to do in this case.
Edges
actually, it's better to label edges here.
It is better. Yes, 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 yes. Can we do it? Can we see how to do it, or is that not? Yeah, we can do
Probably.
it. Yeah, because this is just a graph. This is just a graph.
Yeah, but we need to figure out which edges those are. I mean, we can do it, of course, but it's a bit more complicated. And also, if there are multi-edges, you probably have to do the tags business and so on.
Right. But let's do just one thing just so we get some idea of what we're doing here, okay? So each edge, what is the edge? The edge is between the label for, there's a expression index, right? That's here, right? So what we've got to figure out is what,
yes, so if we take an edge here and then find the input and output events, we can see what shared expressions they have.
right. Okay, so let's just do that, okay? So tell me how to get the input and output events for a given edge.
Well, events list.
So
for a given edge.
Yeah, the 5 to...
Well, there is a destroyer and creator events.
Okay, so then 5 to 11, what are those? How do I find for 5 to 11?
Let's see. Well, you need to take element 5 and 6, or there's 5. Okay, you need to take element 5 and 11 from this list, and then see which one is shared, and the union of corresponding parts.
Okay, so what am I looking at?
The union of the output of the first one with the input of the second one.
Okay, so then let's do the edge list here. Okay, so this is, we're going to have edge labeled causal graph, right?
Yeah. Yeah, so the vertices should just have rule indices and edges expressions.
Okay, so what are we doing here? So here, we've got the events list. Okay, so first thing is we generate the causal graph, I think. Let's get rid of all the rest of this because I don't think it's relevant. Okay, we generate the causal graph. Now we get the edge list of the causal graph, right?
Yeah.
And then for each edge, we index into the events list. Okay, so for each edge, oops, what did I want? Sorry, we index into the events list, right?
Yeah.
Okay, so here, okay, and actually we might as well just strip out, just do the last there. Okay, so now that edge list is for each thing, we give first of hash is, and I'm not going to do the tagging, we'll do that some other time. Okay, well, we're going to do first of this, and that comes from EL help. Help. Okay, I'm going to get in the edge list, right? In the edge list, each edge is a pair, right?
Right.
So what I'm going to do is for the edge list, each element of the pair has EL, this thing,
right,
comma,
and part of,
yeah, it's the second part of that one.
Second.
Right. Goes to.
Second twice because.
No, I already did the last. I already did this. I already did this.
Okay.
I already did the rule index. Okay. So now it goes to EL last of hash, actually we could just do hash 1 just to be clearer here. EL hash sub 2, comma 1. Okay, so that is now those
Wait,
things.
why is it an error? Why is it a rule? It should be a union.
It's not a rule. It's not a rule. It's a union of those two.
Right.
Okay, so that may be over union, but that's all right. So that's to the edge list. And each one of those, actually it's a hash, goes to that.
Yeah, I think so.
I don't need that ampersand. Okay, so then what we're doing is we're saying causal graph, we're saying WMO of...
Okay, yeah. Causal graph.
Now, can I say edge list just here? Edge labels?
Yeah.
Okay. So, edge labeled causal graph of this. So those are, let's go back 3 here. I don't understand this. Those are supposed to be labeled with, the edges are relations.
Can you plot expressions events graph nearby so we can compare? And the vertex labels goes to automatic for 3 steps. Oh, actually, hold on. No, it should be automatic. Yeah, so these are not atoms, definitely there. So I'm not sure what it is. Something's wrong. Yeah, let's look at each labeled causal graph.
Well, look, I need to get to some other things here. So, I mean, you could work on unscrambling this. I think what we want to do,
Yeah.
let's just, I mean, okay, let's here, okay, edge label causal graph. Let's just do the obvious thing. Okay, so this is the events list, right?
Did we ever extract the contents of those events of expression? I don't think we did.
No.
Because there are no expressions anyway.
We didn't. We just asked for the events list, and that's a list. So I don't know what the elements in that. Those things there. Those should be atoms there, right?
No, they're not atoms. They're expression indices. But I don't see why we have lists of 4. We should have lists. Oh, it's not a union. It's intersection. That's problem.
That's a key problem.
Right. Okay, so that's probably, yeah, I think it's correct. But it just shows you expression indices.
Right. So each edge has one expression, and these ones, because they're double edges, they have to be split apart.
Yeah. Yeah, but now you could just, before intersection, you can put WMO of all expressions part that intersection.
What will that give us?
All atoms content.
Oh, I see.
And all expressions is instantaneous. You don't need to worry about performance. Yeah.
Well, apart from the silliness of the stacking.
Oh, you can also map to stream over it. Oh, no, you don't need to map it, just to stream before expressions.
Why are there two levels of braces here? Oh,
Because it's hold on.
Yeah,
Why
it's because
it?
we haven't broken them apart with the different tags.
Oh yeah, right.
So that's showing us which is the actual relation that is needed for the next event, right?
Yeah.
Okay, so the causal graph is an events relations graph. Events relations graph. And the selection is all. Well, all for a particular updating order, right?
Well, the way it's implemented now, no, it's all, just all.
No, but that would be a multi-way causal graph. It's not a multi-way causal
Right.
graph.
Well, it can be if you run a multi-way system.
With your new local multi-way stuff.
Yeah.
Okay. Okay, so that's the basic causal graph. So now, the next kind of graph that we have is probably the dual of the spatial hypergraph, which arguably we should put up here. Dual
Right.
spatial hypergraph.
Expressions atoms graph.
Where the vertices are relations and the edges are elements. Okay, and the selection is the same as basic spatial hypergraph. Okay, so we had definitions for this someplace. This is this one here, right? Is that right?
Well, let's see.
No, I don't think
It's expressions spatial hypergraph.
Is that right?
Yes.
State edge indices after events. Why does it have anything to do with events? We don't need to know anything about events to do this.
It's the final state. H index is the final state. It's event -1, the last event.
Oh, I see. I see.
Yeah, it is this one. I looked over it today. I have an issue with, I even copied this code in it.
Okay. So let's well, we might want to call this
Expressions atoms hypergraph.
relations elements hypergraph.
I thought we agreed to call them expressions and atoms eventually.
I like relations and elements. I mean,
The problem is elements, it's very generic.
it's
So
very
it's,
generic.
well,
It's very,
exactly, which has the same problem as vertices. It's when you're talking about something, it's possible that by elements you have to mean something else, and then you don't know what you're talking about anymore. Whereas
well,
atoms
maybe we should
never appear anywhere.
call them as relations and atoms. Well,
Okay.
anyway, okay.
So
Okay. Anyway, so this let's for now we can say elements events hypergraph, and then we take this thing. Oh, whoops! Now we also need
an ordered hypergraph code.
okay. So vertex labels arrow automatic is not necessarily going to give very sensible vertex labels, is it?
Well, this
Oh,
are
we don't want.
expressions.
Yeah, which is really hopeless.
So I guess
those should be labeled with relations, or
no, the hyper edges need to be labeled with atoms.
yeah,
To
right.
be consistent with what I did before, which is going to be a lot more difficult.
Okay, so then we've also got this guy here. What is this guy here?
Events causal past graph. Or common, events common past graph.
And this is again a purely spatial graph. This is.
Yeah, selection is.
Okay, hold on. Okay. Events, common history, graph. No. Event spatial graph. I think we should call this probably event spatial graph.
Well, then it's ambiguity because spatial might mean shared atoms.
All right, events common history.
And you definitely can connect events by shared atoms.
Okay.
By the way, shouldn't this events common history graph should also be a hypergraph?
Okay, hold on. There's another event. There's another graph then, which is events shared
Events atoms hypergraph.
Well, it's events shared. Why isn't it events shared relations hypergraph as well as
Events shared relations is a causal graph.
Okay. So that's AKA events.
I guess in a multi-way system, it's actually a partially directed hypergraph. Technically speaking.
Events shared relations. Graph.
Yeah, the multi-way causal graph is actually a hypergraph. I didn't think
multi-way
this way
causal
before.
graph. Why? Because the multi-way
because
causal...
the same expressions can go to multiple events. And it's neither undirected or directed. It's well, its first element is important. The rest are undirected.
Okay, so let's say events. Okay, wait a minute. Then we've got the events shared atoms graph, right? That's this one. Is that right?
No, it's not this one. It's a different one.
Christ, this is so complicated.
Oh, there are 20.
At least.
Oh, 20 elementary ones.
Yes, and there are even more when they're composite ones.
And then times 4 factorial. Oh, not factorial. So more. No, I don't know. Number of subsets.
Right, which is 2 to the n.
More or less.
All right, so this is...
minus 1. Right.
Yeah, minus 1. Okay. Events, common history, spatial graph. So this one, its vertices are events. Its edges are common history. And its selection is same as the basic hypergraph, right? Same as basic spatial hypergraph, except on events.
Yeah, right.
Okay, so here we can do the same thing. One step of history, and then we have 2 steps of history. Okay, events, common history, spatial graph. Okay, was there another kind of spatial graph that we had?
Events, common future is an obvious one.
What's the event shared atoms graph?
Well, events are composed of expressions. Expressions have atoms in them. You can check if the atoms are the same.
Okay, but that's a causal family graph.
Why?
Because it's going to be a space-time graph. This one is okay. Events, common future. spatial graph.
The same atom might appear in many different places.
By the way, did we already do this common feature graph?
I don't think so, but it's not. Well, no, it didn't. We only have common past.
What color should the edges be here?
Oh, that's
These
a
are
new
sort
color.
of branchial edges. Yeah, right. It's a common.
Yeah,
Okay.
it is branchial. It should be purple.
I don't think they should be completely purple because we want to keep those as kind of.
It's exactly the same thing.
I know. Somewhat branchial. Need new color. Somewhat branchial.
Why somewhat branchial?
Because I want to keep the branchial thing to mean a distance in state space. This is a distance in space. See what I'm saying?
Isn't it? Hold on, isn't it the same distance? Because edges in the state graph are also events.
No, connect events. But this is here. Let me. How do we get the branchial color?
Well, there's branchial graph edge style in the Wolfram Physics Project style data.
What is it called?
Branchial graph. No, the first argument is branchial graph.
Yeah.
Edge style.
Why isn't the spatial graph got an edge style?
I think it's a hyper edge style. Hold on, it might be multiple. Can you just delete the second argument and it would give you association? Yeah, it's edge polygon style and edge line style. The two.
What was it called? Edge? Oh, the other one was called branchial graph edge style, right?
Yeah. Have extra n in branchial. Oh, wait. It's, yeah.
Okay, so here this thing gave.
So if we do this events common history spatial graph for a multi-way system, would you then say it should be purple?
Yes, I think so.
So the purple, I mean, the fact that it's purple has nothing to do with the type of the graph. It's whether it's a multi-way system or not.
I think so.
And I would imagine branchial graph might have to be blue as well then, if it's for a single way evolution.
Whoops.
So I guess we have a fourth parameter for graphs now, whether it's a single way or multi-way evolution.
Okay.
Okay, it's not 20, it's 20 times 2 at the very least.
Yes, right.
And
Okay,
times
okay,
2
wait a
again.
minute, wait a minute. Construction method is
Well, it's well, sure.
I
I wouldn't say it's a method because the result is different. It's more like
okay.
a system type.
All right, so events, common history, spatial graph. Okay, what other types are there that we've already identified, that we identified previously? There is oh my God. What other things are there? So that's in those things.
Yeah, I think that's it for this notebook. And for set replace as well. But the multi-way system has more.
Well, but
we didn't mention branchial graph yet.
no, I know, because that's yet a different. I didn't mention evolution events graph either. I mean, because
Well, that's a whole different situation. That has to do with identification.
No, I'm sorry, expression events graph.
Well, expression events causal graph, I guess, is a new full name. Yeah, but that's not that different. I mean, it's just
it's relations
two graphs in one.
Plus events causal graph. By the way, in this puppy here, those things there should be the color of, well, you did polygon edge style. I guess that might be right, because those are the, yeah, that might be right.
Actually, I don't remember where did the styles come from. They're probably the same. No, I'm pretty sure they're the same. We should flip them. Vertex style should become hyper edge style and vice versa.
From this?
Yeah.
Okay, well.
I don't think they're flipped here.
Okay, we should flip vertex and edge styles. All right, listen, the thing I wanted to do, I want to just look at, I'm glad we've got another color here. That's exotic. God, we have to remember what all these things are. Okay.
Well, if we have consistent names, I think we will remember.
But so this thing here is a decent proxy. This is one of the proxies for space.
Yeah.
Is that the main proxy for space we were using here? No, we had a different proxy for space, which is this thing here, right?
Atoms graph. Yeah.
Okay, all right. So what I want to do is I just want to look at all these proxies for space. And I simply want to ask, what the hell do I want to ask? I want to ask, if I look at the effect of a perturbation, I just want to look at the geodesic distance. This is what we were doing before, right? The geodesic distance in the final graph, right? The shadow of the causal cone in the final graph. What is the geodesic size of the causal cone, right? That's the key thing we want to figure out.
Yeah.
Key question. Geodesic size of causal ball in spatial slice. That's what we want to know. Want to know how that geodesic size. Okay, and so the question then is the boundary of the causal ball uniformly growing in geodesic size, in geodesic distance from its center, whatever that means. Okay, so alternatively said, okay, if we had our ordinary spatial graph, what is the size of the geodesic ball in that? That's the number of events. That's simply the atoms affected by a given event, right?
Well, I would say expressions affected by a given event.
All right, okay, fine. All right, so ordinary spatial graph want to know the relations affected by a previous event. Is that right? Yes, that event has consequent events. Is it an event? Yes, I think it's an event. Is that right? What that event
well, it can
causes?
be an event. It can be an expression, doesn't matter.
Previous event or relation. Okay, that's in the ordinary spatial hypergraph. So then we also have we can ask the exact same thing for these other kinds of graphs. Why did we want to do it for this graph? Why did we want to do it for
Well, because we have expressions in the other graph. These expressions common past graph. So we wanted to have.
But why do we care?
We have expressions as the verses there, so we wanted to have expressions as the verses here as well.
But why are there two different graphs? Why aren't we just looking at how an effect, how the light cone?
Yeah, we don't need two different graphs.
Yeah, I don't think we do. I think we just need to look at the ordinary spatial hypergraph.
Just use atom expression graph.
Right. Okay. All right. So let's work out, and I think we did this, didn't we? Okay. So pick an event. Okay. So what we want to do here is pick an event or a relation, whatever you want to do. Pick a relation. I don't care what it is. Okay. Pick e.g., a relation at step t and see what relations it affects at step t prime. Okay, that's what we want to do. Make sense?
Yeah.
Okay, I need a little piece to eat. I will come right back and let's do this. If you can think about how to do it for 1 second, I'll be right back.
Okay.
Okay, all right.
Well, I think we did it already. It's called effective spatial ball.
Where did we do it?
Let's see.
Here we go. But that's something different, isn't it? I mean, that's the... It is. To deduce the effective spatial ball from the genuine light cone. All right. What does that mean, the effective spatial ball? So that means after n steps, what is that returning? What are those indices?
Expressions.
Okay. Oh, so what we should be doing, what we were not thinking properly about, We can either draw those expressions in the dual. Okay. These output IDs are relation IDs. So we can either draw it in the dual thing.
We can draw it anywhere. If you get final, well, we can get the atoms from all expressions, and then we can just do graph highlight with those lists of atoms on final state plot.
Oh yeah, fine. Let me just draw something. That's for my edification. Is that the initial state, that thing at the beginning? No, I think it's one step
no,
after the
it's yeah. Right, that's correct.
That's a useful plot, in my opinion. That thing like we just generated there. So this now, I'm being stupid here, but I'm just doing it for the sake of being able to have something comparable. I have a distinct feeling that we've done this before.
Well, we did it before, just not with this graph.
Well, wait a minute. Did it before? You mean yesterday, or like?
Yeah.
No, I'm just
Oh,
gonna.
before yesterday. I mean, maybe we did it, but I don't remember. I mean, I did it before during summer school, probably, or I mean, I did it sometime. I don't remember when. Yeah, it was Chris' project in the summer school.
Which Chris?
Chris Pratt. With searching for particles, and as part of it, we did this kind of plot.
All right, let's go. Oh, I just want to draw. This kind of plot. Well, that's interesting. Okay. So, I mean, these graphs, we could compute. Is the effective dimension of this graph likely to be the effective dimension of the same? And it is likely to be the same as the other effective dimension, right?
think so.
Okay, so let's go down here. Okay, how do we get the atoms out?
Let's see. Well, all expressions property.
Okay, so here we say what? Sorry. What you're saying?
All
This
expressions property. Yeah.
Okay, so we do this thing outside of this whole thing. We say WMO of all expressions of this intersection. Is that right? And then we flatten it. Is that correct?
Wait, why do you flatten it?
Because we want the set of atoms, right? Those are relations.
You don't need, if you want to highlight them, you can highlight lists of atoms directly. You should highlight expressions.
Okay, like that, you mean?
Yeah, so you can pass it directly to highlight graph.
But not a graph, it's a
Graph
hypergraph.
highlight. Well, it has an option.
Okay, so how do I do that then?
So you can do final state plot property. Yeah, and then say graph highlight goes to this list.
Okay.
Yeah, and if you want to highlight vertices as well, you can also do join this %11 with union of catenate of the same list.
Okay, all right, okay, okay. Okay, so then if I say effective spatial ball plot of WMO x per 0 is WMO x per 0, and then I want to take WMO, actually I want to say with BB equals, then I want to say WMO, a final state plot graph highlight, arrow, join of BB, comma, union of catenate of BB.
Right.
Okay, if I go like 7 steps there. Okay, now how do I pull back? How do I choose an expression on a later step? Do you understand what I'm saying?
Well, that's tricky because there is no state edge indices at generation. Oh, actually, hold on. You can, right. If you specify generation, you can get generation's full expressions, and then you can just pick random expressions from that.
Okay, all right, okay. So let's say, let's have a function that's called generation relations of WMO, comma.
It's state edge, well, anyway.
What's that? Well, hold on. Generations relations, which might as well be for the final state there.
Well, why the one for the final state? We need the previous state.
No, because I'm going to use a different number here. I'm just going to pick
Well, okay,
some.
if you don't mind recomputing it, then it's easy because you can just use state edge indices after event -1. I mean, the whole function would be just WMO of state edge indices after event, -1.
Okay. Okay, so it's final relations.
Yeah, I really need to work more on these properties. They're very lacking compared to evolution.
Okay, let's say step 4. Okay. So now let's go to step 8 and pick one from step 4, let's say 32. Dandy. Okay, so now if we go to step 9, okay, step 10, so how do we find out? So what we want to compare is this light cone output with the whole size of the space, right?
Whole size.
Well, actually, we want that subgraph. We want the size of that subgraph. We want that subgraph. How do we get that subgraph?
Probably just the length of what you highlight.
No, that's just the size of the subgraph. I want the actual subgraph.
Well, that's what you highlighted. Pretty precise. I mean,
No, I understand, but I want it as a graph if I can get it.
As a hypergraph.
I guess as a hypergraph, yeah.
Well, yeah, that's exactly the argument for that option, for graph highlight option.
I see. So that's exactly what.
Yeah, graph highlight just takes the contents of expressions, which is a subgraph.
So the effective spatial atom ball.
Yes, that's a sub-hypergraph.
No, it's the effective spatial ball. Right, so if we want the effective
atom
spatial...
ball.
No.
Spatial ball is and just have indices of expressions.
Oh yeah, okay. Effective spatial atom ball of this. Okay, so it's this, comma, this. And each one of these, so let's say T here. Okay, so for each one of these, we want to plot. How do we plot the hypergraph that we're getting out from these? We just say resource function of hypergraph
Model
plotters.
plot.
What's that?
Wolfram model plot.
Okay, so let's say T, I don't know, let's say 5 to 10. Let's see what happens if we go below that. Let's say we say 4. If we go to 3. Okay, fine. That's what I would expect. Okay. So those are the light cones that we get to. Those are the light cones. So what we want to determine...
These are sections of the light cone.
Yes. So the question is, let's say we take, let me just go to slightly larger. Okay. So this is a picture of what parts of the spatial hypergraph are affected. Okay, so the issue here is, if I look at this thing, and I'm measuring space, I'm measuring the space across this, right?
Okay.
I measure it with geodesic distance. So let's say I just take this thing here, and I measure that. So I make that into a graph. I think I have a function, hypergraph to graph, don't I? Okay. So now I make that into a graph. And actually, I want to make it into an undirected graph, because that's the way we've been thinking about distances. Right?
Yeah, that's not quite right, because that won't give you distances if there are hyper edges.
Oh, I know that. I know that. I know that. Don't worry about that for a minute. Okay, so that's this. Oops.
T is undefined.
Oh, yeah, yeah. Okay, so these are now graphs, undirected graphs. So the question is, what is, so if I say graph diameter of these guys, oh gosh, what does this mean? See, because the problem is two things are happening. the universe is expanding at the same time as the light cone is expanding.
Yeah.
So I don't quite understand that. I mean, it'd be better to have a rule where that wasn't happening, where the light cone expands, but the universe does not. I mean, not as much. Would that happen?
You'll need to have the same number of inputs and outputs.
Yeah, and then we have to start. Okay, but if we had the same number of inputs and outputs, okay.
I mean, for this rule, I guess we might generate it for a few steps and then delete two of the edges from the right-hand side.
Yeah.
That might give us something.
For non-expanding rules, can look at light cone independent of expansion of the universe. Okay, so let's take a look here. So let's say we go 7 steps and we go to the final state. Okay, fine. Okay, all right, now let's imagine that. What would you do here? Do we not want to generate a new atom, or does that not matter?
Well, it wouldn't grow even if there's a new atom.
Right.
But, well, I don't know, let's just try it.
Let's delete the second 2. What is it called? Plots? What is that thing called? What's it called when you're making a list of plots? I want to make a list of plots.
It states plots list.
Oh, they fall apart. Okay, so we need a connected right-hand side. What do we do to get a connected right-hand side?
Well, it is connected, but well, let's just try all this. Actually, well, let's just try all these combinations. Maybe one doesn't work, but it might be because we are creating a new atom.
I think it is. Let's go. Let's see, what would it be? It would be YZ X. Let's try YZZY. A little wild, but not totally crazy. I mean, some little pieces fall off the universe.
Because you forgot X. So it deletes atoms eventually.
All right, fine. The universe is blobbing around.
Right.
Okay. Okay, so now what we want to do is start off with even a bigger universe. But now, instead of doing this, what we want to do is we want to make these guys Okay, so from an expression in here, well, and wherever we get to, right? Let's say all right, so let's take a random choice WM9T. That's our initial, I don't understand. Is that an expression? No, what the heck are we doing here? How do we find out the initial, how do we find out the expressions that are available? Oh, we want to use this expressions relations, right? Final relations. Final relations. Okay, let's do a random choice on that. Okay, so now say T there. We want to have this rule there. Now we want to say WM9T there. Oops, we want a close brace there. Okay, so let's make a table here. T goes up to 6. Why does it say that? I don't understand that.
Is it because T is too small?
No, because even in the initial state, that must exist, because that's the whole point. That's what we just did with the 9-step thing. But that expression exists in this. Well, wait a minute. How do we know it's expression 991? It's got a differently indexed expression number here. All we fed in here was the atom lists. You see?
Well, right. Yeah, let's see. Well, you have to select expression from these ones. You cannot select expression from before the evolution started.
Yeah, right. Okay, so what I've got to do is I've got to say,
You could just try expression 1.
yes.
Or random choice from the range of the lengths of the initial state.
Why is this so comparatively slow?
Well, it doesn't. Let's see. Well, the radius of the output is smaller, for one thing. Well, the volume of the output is smaller, so of course
Which?
it grows slower. The volume of the output is smaller, so of course it will grow slower.
No, I understand, but why is it running slowly?
Running, well, I don't know.
Because it's not generating a lot of edges, is it? Is it generating more edges here?
What do you mean?
As this evolves, it doesn't generate more edges, does it? It's just rearranging edges that are already there.
Well, during the evolution, of course, it changes more edges, more expressions.
No,
but I don't think it's a slow part.
But not during this part here. I don't understand why. I'm confused here.
I think the slow part is plotting.
What is it doing wrong here?
I think you need to do partial evaluate, get, set, replace.
Oh, God. But that should have been done a long time ago, right? It doesn't. Is it not up to date?
Apparently not in other kernels. Which is strange. I mean, if it evaluated
Well, maybe Roger maybe Roger didn't do it correctly.
No, did what?
Update the packlet.
I don't think the problem is it's not updated. It's just not running at all because Wolfram model evolution object of property is not evaluated.
Get what?
Set replace. Like a spec tick. Okay, so now it's not updated.
It's crazy. How do I update
Can you do
it?
parallel evaluate, packlet, install, set replace?
Backtick or not?
No.
Then do I have to redo the get?
Yes.
Wait,
why is it different? Some of them 0.2.120, which is very old. Do you have the same kernel version everywhere?
I haven't a clue.
Or if you do parallel evaluate, taller version.
I know. I'm not going to debug this right now.
Okay.
I'm going to let Roger debug it. It is his job, not mine. Some difference, but this.
Well, it's 12.1, which is the important part.
Okay. In any case, okay, we can't do this necessarily, but so to measure the size of this light cone, right, for which we don't necessarily have to plot, how do we measure the size of this light cone? We just say effective spatial ball of these successive things, right?
Yeah. Can give you length of it.
That's going to be the overall size of that light cone.
Yeah, number of expressions in it.
That's growing rather rapidly.
Oh, but I think I know what happened. It's probably not set replace was outdated, but the resource function was outdated. And it installed the old set replace while it was running, and then it broke everything.
Yeah. Okay, but so what we have to do here is, the goal is to find how the light cone expands in something where, okay, the system is blobbing around. You know, we could just take a grid and we could do updates on the grid. And then we're asking the question, let's see, how do the causal updates compare to the geodesic distances, right? That's the big question. Does that make sense?
Yeah.
Because the causal updates you know, is there a particular path we can follow down the light cone that leads us a longer geodesic distance away? Now, the geodesic distance is essentially
Well, there is for past common history, or there is for common history, as we figured out last time.
What do you mean?
Well, we had this, claims last time about which one can or cannot be larger. It's probably faster than light or two.
No, I know, but I don't think that claim. Let's review that again, okay?
For the common history, it was possible both ways. Not for the common history, it was possible both ways. For common future, it was only possible one way, which I still think is true.
Well, wait a minute. What are you saying? You're saying
so we have two kinds of causal balls. We have the history one and then the future one.
I see. Okay.
So for the past one, it was possible to have one ball larger or the other ball larger.
Okay, hold on. So the issue is, case one is causal cone from the past. Case two is causal cone to the future, right? So that's saying, and the claim for the causal cone to the future is,
so with respect to causal cone of the past, the question is, can you travel faster than light in terms of current space if you came from the past? And the answer is, of course you can, because immediately after the Big Bang, you can travel, somewhere close to the speed of light. And now, if you look at the same distance, but in modern space, which has expanded by now, that would be faster than light.
Sure.
So that's why I think
Okay,
causal
hold
conform
on,
to
hold
past
on.
is not
Well, but I
the
mean,
only one.
the universe could be contracting too, so that argument doesn't really wash, right? So I mean,
But I'm saying there are universes in which it's possible.
no, but okay, hold on a second. So it is easy to go faster than light with respect to current.
Actually, it's a good point. If it is contracting, then you can go faster than the speed of light according to modern space.
Right. With respect to current, it's easier to go faster than light. Well, let's walk through this argument again, okay? So, okay. Imagine you go a certain distance in the early universe. No, I've not understood that. Okay. I see. Imagine you go a certain geodesic distance. No, it isn't a geodesic distance.
Let's see. Well, if you put, beacons at the fixed positions in the universe, and then
Sure,
they never move.
Right. Set up beacons in the early universe. Know how long it takes then to go between them. Now, compute speed based on current beacon positions. Speed then, measured using current distances, will seem to be greater than c.
Right. Well, that should be in the causal con from the past section.
Okay.
Yeah, and you can do the same thing with causal con the future if the space contracts.
Right. Same story as with past if space contracts. But I don't think this is an interesting case. I mean,
isn't it? You can make a highway which has contracted space in it, and you can travel through it very quickly. Which I guess it's a different idea from the wormhole. Well, it is different because it's different topology.
well, so you're saying, and by the way, space does contract around a collapsing black hole, doesn't it? i.e., set up a highway, a space bridge, what would it be called? A space tube made of metal. Then let space contract around it.
Inside it.
Well, and around it, inside/around it. Then the claim is, but there's no sense. It doesn't matter. I mean, the space, the galaxies that were in the space. I don't understand this. I don't understand this. If you
But
are
just less space in the tube than outside of the tube.
so
So you go through the distances in the tube are smaller than outside of the tube. I mean, in the case of network, it's very easy to see. You have, let's say, you have a grid graph, and then you delete a part of it, and then you insert a sparse grid graph in it instead.
sure. Right, so let's look at
And
that.
of course, you can make, I mean, the sparsity of it's only defined relative to something. So,
Right, well, that's basically saying there are long-range connections.
well, not quite. Kind of, but not quite.
Well, okay,
I
so
mean,
let's smash some of these. Okay, let's smash some things in here. So let us do a delete edge. Whoops, edge delete of this. I think they have pairs, right? So let's delete a bunch of edges in the middle. So let's say table, let's say random integer, let's say 35,
well,
45 to 55.
it's not random. You need a neighborhood graph. If you want to do a highway, it's not the same as long-range connections. Because
No, I
they're not
understand.
really long-range. They're just
all right. So I want a neighborhood graph.
Long-range.
I want a neighborhood graph of in that grid graph.
Yeah, I mean, ideally, we want to make it long and thin, but I guess it's not really possible.
Neighborhood graph of G, comma, let's say, I don't know, 25, 25, is that in the middle? Comma 3. Let's just see what that does.
Are you sure they're lists?
Thought they were. Oh, I'm wrong. Okay, so what do I want to do?
Look at graph center. First of graph center. And probably edge list in front of neighborhood graph.
Okay, why does it do
this? That doesn't make any sense at all. You know what? As an experiment, can you, in front of grid graph, can you put graph of edge list of grid graph? Okay, we found a bug.
What is the bug?
I'm not sure, but sometimes neighborhood graph of grid graph doesn't work. And I tried to reproduce it and I couldn't, but.
Okay. Okay, so let's now go. I see that little solitary vertex down at the bottom is a disconnected node.
Maybe we should graph complement.
Where?
Instead of edge delete. I don't know if it gets rid of vertices.
But then this has to be a graph, right? Not edge list.
Yeah, I think so. Huh. Oh, that's a different complement, I guess.
Is it graph
Oh, no.
complements?
Yeah, probably. Yes.
This is unbelievably slow. It's probably doing some weird isomorphism checking. All right, so let's do edge delete of edge list, and we can get rid of the, I don't know whether we care about those other little random bits and pieces. Okay, so that's that. Okay, so now to be sparser about it, actually we can make a bigger, let's make a bigger hole. Okay, so now to be sparse on our highway, we would say, instead of edge list here, we would say random choice, random sample. I think random sample actually takes a scaled argument, if I'm not mistaken. Huh. Well, anyway, how many do we, what fraction of these do we want to take? Let's take a random sample of 50 of them. What?
Well, you just didn't delete all of it. I don't think random sample is going to work because that wouldn't make any distances shorter. It can only make them longer.
I see.
Yeah, so we need to actually make a sparse grid and insert it there.
I see, and then glue it.
Yeah.
Okay. So.
But more realistically, the way it works is that, so the scale is only defined relative to something. So you can just take an ordinary space and put it in that highway. And as long as we can connect it to the outside space so that it's stable, we can do it.
Yeah, exactly. So the question is what configuration of matter, so to speak, we need to make that stable.
Yeah. There are definitely going to be strong gravitational effects at the boundary.
Right, but the important point is that in these graphs, right, okay, let's just walk this through another time, okay? So if we have a static graph and all our update rule is doing, it's not changing the graph. All the update rule is doing is moving markers around on the graph. You see what I'm saying?
Yeah.
we can still get faster than light travel along our highway, right?
Right.
Then the question is, can we maintain the highway?
Yeah.
Right.
I guess the only real difference from that highway and the wormhole is that you can merge onto it from anywhere along its length.
Sure. Sure, but in other words, you have much more bizarre possible things happening because you can have arbitrary dimensional space there.
Well, you can, but you wouldn't want to.
Why?
Well, because you need to be able to get into it and not, you know, and be able to survive in it. So, you know, so the entry points should still be normal space.
Well, it doesn't matter if you're just trying to communicate, you don't necessarily have to survive in it.
Well, okay, fair point.
Right. You know, does the interior of the tunnel have to be ordinary space?
Although it does sound a lot more expensive than just a wormhole. Because it would be long.
Right. But by the way, I mean, we should be able to just make wormholes easily enough here. I mean, we just make non-simply connected graphs, and that's easy enough.
Yeah.
Does the interior of the tunnel have to be ordinary space? Yes, if we want ordinary matter to pass through it, but no, if we just want signals made of something to pass through. So, okay. But now a higher dimensional glued piece in the middle there. If we just have, okay, so if we just have markers moving on the space and we are not updating the space, that's a idealized case, right? Just have markers moving, we're not updating the space. That's one case. And in that case, then we want a lower dimensional interior. Is that right? To the space tunnel. Is that right? Is that right?
Right.
We want a sparser edge interior to the space tunnel so that it takes fewer edges to go from one side to the other, right?
Right.
Which could potentially be achieved with a, but okay, so look, we need some code to glue graphs, okay? So that we can do experiments like this. We also need a thing where we can glue a higher dimensional lump inside one of these graphs. So, okay, so how do we do graph gluing?
Well, it's not that simple. I guess, well, Well, in a one-dimensional case, if you just have two paths, we can join them by identifying vertices in them. That's not too difficult.
Yeah. But in
a
this case,
two-dimensional case, though, it's you would have to put one surface on top of another one, which is not that straightforward.
okay, but look, this is one case, is we've got a fixed structure of space, and then we move markers around on the fixed structure of space, and we have to try to maintain that fixed structure of space somehow.
Yeah.
Then we've got this case where you haven't built a highway. And instead, you're looking at what we were looking at before, which is see, I think it's complicated because I think in both cases, what you're doing is you've got two moving parts. You've got the space is changing underneath you. I think if the space doesn't change underneath you, then you're right. There's basically a theorem that you can't go faster than the update speed, than the update distance, right? If the space doesn't change, that's
right.
kind of obvious. If the space does change, update distance per the rule diameter per elementary time, right? That's kind of clear that that's got to be the case.
Yeah. The space does change. It might move towards you.
Exactly. If the space does change.
But the point is, it's not up to you as it moves to you or not, because...
Absolutely. It's not up to you. That's right. That's what I keep on saying. That's why I'm talking about subspace demons. Right. But it is not, but it is not under your control whether the space, quotes, moves towards you.
Right.
Except that Alcubierre metric claims that it can feed space into you. But I suspect the negative mass character of that has something to do with the way that works. Okay, so I think that's just basically saying, by putting that negative mass there, it's basically just saying, I'm going to make the space move towards you. So
yeah, but it still has limited influence.
What do you mean?
Even if it's negative mass, it can only interact with the space nearby.
Well, we need to understand this Alcubierre metric, but what this is basically saying is,
well, I need to understand it in terms of ordinary chair first.
I know. Well, you should look at. I'll send you Jose's notebook about it. You know, we should do more of these studies of how sort of existing physics questions relate to the models. I mean, we really do need to nail the Casimir effect, because that's a story of negative mass. Right?
Sure.
And I think all it is limiting the size of the system. I mean, like I think all it is you know, breaking our strings at different places, so to speak. Yeah, I'm pretty sure that's what it is. And I think it's just the number of causal edges that you get. You know, in look, I think Casimir effect for a 1D string, basically imagine there are markers that prevent interchanges in some places. So I'm going to make the following claim. So this is going to make a causal graph Could it be this easy? Well, it really should be an infinite string on both sides.
Well, I think I understand what your point is, but I don't know. It seems it's oversimplification of it. Well, what you're saying here, if you have a run and walk, and there is a boundary, then there is an effective force that moves it from the boundary.
Yes, that's what I'm saying. And it's the same phenomenon because it's basically the number of modes. It's a mode counting story. And mode counting for us.
Well, actually, yeah, maybe it is.
Anyway, I think something like this is right. And this then has fewer causal edges than it would normally have.
Yeah.
So this question about whether it's under your control whether space moves towards you. So there are two basic issues there. One is, if you look at different branches of quantum history, is it just different on each of those branches? So that basically there's no classical way to achieve this. The different vacuum fluctuations will achieve it, but you can't make it classical.
Right.
you know, so
I'm really confused by this Hypergraph because you need to be able to send information about the fact that you have a negative mass somewhere faster than the speed of light.
Look, I don't understand the causal. I mean, I don't know whether anybody has causal diagrams for it. Okay, so there's a claim that warp bubbles could be used to create closed time-like curves. Okay, so the claim is, okay, can FTL be used to create closed time-like curves?
Well, you can pick a reference frame in which you would go to the past by doing FTL. So if you then do an FTL again back in the reference in that same reference frame, you will get to the past. So let's say we have a cosmological frame and you do FTL in that cosmological frame first. But if you look at it from the boosted frame, you might go to the past. So you go somewhere during this method, then you boost yourself so that you're now in the boosted frame, and then you go back. And this way you will end up in the past from where you started.
By going to the boosted frame where it's an FTL boosted frame.
Yeah, so you do FTL, then you boost, and then you go FTL back while boosted.
Okay, so wait a minute. You're considering an FTL boosted frame. I mean, that's a pretty bizarre thing, because an FTL boosted frame is a tachyonically boosted frame, right? So it's already got some messy stuff.
Hold on, that's not what I'm saying. If we have a symmetry with respect to the boost, which we expect to have. Then we can do FTL somewhere, then accelerate, and well, to a different speed, so that we are now in a boosted frame, and then do an ordinary FTL back while in that boosted frame. Because we have a symmetry with respect to the boost, we can do that.
I'm not certain that symmetry exists, but yeah, okay, fair enough. I mean, that should be mathematically.
Well, it exists in GR.
Sure. Look, the fact is, what we don't know, if you could ride the vacuum fluctuations, I mean, I'd like to actually make a picture of this, but I'm pretty sure you can go we need to make a picture. I mean, we need to make a picture, and I don't see how you do it in terms of the causal graph. We need to make a picture in which we've laid out the causal graph according to its position in space. If we can do that, then you can see that there are causal edges that will take you further than the average light cone. Do you see what I'm saying? If we lay out,
Sure.
look, you know, so right, lay out a causal graph so that its nodes are, quotes, correct geodesic distances, then simply look and see whether there are causal edges that are going faster, right? So in other words, we could just take, if we take way back here, we take this causal graph, okay? Take this causal graph, okay? Now we lay out those, we use the events, oh my God, I'm so confused by these things. The events common history graph to determine a geodesic distance. You see what I'm saying?
Okay.
Right? Then what we have to ask is, do any of these causal edges, okay, if we lay out the events according to, yeah, we can do it. It's just from this graph, right? According to the geodesic distances of the events common history graph, right? Then any causal edge going at, quotes, more than 45 degrees, oops, is an FTL edge. Does that make sense?
Okay.
Do you understand the claim?
Yeah.
So how do we lay out this graph?
But that assumes it's possible to lay it out this way.
Well, it's always possible to splat things down somewhere. I mean, we can just ask the question. We just by fiat, put those things at their geodesic distance. Right, pick it.
Yeah, but we cannot do it for all vertices, generally speaking. At least not in fixed number of dimensions.
Oh, I see what you're saying. Yes, you are correct. Yes, you're correct.
But roughly speaking, is this correct?
Right. Right. So it's the correspondence between the causal trying to make space sensible. I'm sure that there are fluctuations that go outside of that. But I really want to make a picture of them. Really want to make a picture. How can we make that picture?
Well, we need coordinatization of space for that.
No, we don't. No, we don't. Look, here's the way we do it. We simply compare we're simply comparing the light cone, okay? We paint a light cone on here, okay? And then we paint a geodesic ball on here, right? That's all we have to do, right? We've got two things we're doing. We paint, compare.
Okay, yeah.
Painting a light cone and painting a geodesic ball.
Right.
All right, now we did that like way at the beginning of this whole thing, right? We painted a light cone on that thing. Let's go find the painted light cone. This was from an expression events graph, but we don't even need that. We can just do everything in terms of the causal graph.
Sure.
And then what we want to do here, right, this is what we want.
That's the light cone.
That's the light cone, right.
Wait,
and then
I don't know why it says fake light cone. No, it is a light cone. It's vertex out. Actually,
no, this isn't. This is the fake light cone. This is the geodesic ball.
Yeah.
So this one, that's the geodesic ball. So we didn't call it spatial reconstruction anymore. We call it, oh, we do call it spatial reconstruction. But it's going to be purple. Okay, so that's the geodesic ball. So now, which we could paint on this graph here. Right, we could start at that point and we could say, how far out is that geodesic ball going? Now then,
well, that's what we did last time.
well, so what did we conclude?
Comparing these two balls, just not, I mean, they're not, we're plotting them on the balls themselves, not on the causal graph.
Right.
Well, we concluded that I'm not sure what we conclude. Well, we need to compute the speed of light first before we.
But the only way we can compute the speed of light is by having these things go Okay, so here, just to be clear, we could color in purple or something the geodesic ball.
Right.
Right? Now we have to match the geodesic ball on average to the light cone. How do we put the light cone on here? Sure, we had one of those up here. Did we? How do we put a light cone on this? It's the vertex out component of a random thing, right? It's just highlighting the vertex out component. I don't know, 6 or something. Doesn't matter. It's just some particular node, right? All right, so that's a light cone. Let's go from a couple more steps. Oh, for goodness sake. Layered causal graph, right? And now I want to do that. Okay, so there's a friendly light cone. Actually, it's not very friendly. It's a big mess, if you ask me. Let's try going. All right, so there's a friendly light cone. Okay, so now that's to be compared with the successive areas of geodesic balls here, right?
Yeah.
And, you know, most likely that edge is going to jump outside the geodesic ball.
Well, it's not obvious to me.
It's not obvious. It's not obvious. Okay, so let's paint the geodesic balls. So what are the geodesic balls? So the geodesic balls are the spatial reconstruction graph which, oh God, has its own geodesic distance, which depends on the time it's been since it's been reconstructed. Could we make a light cone in the expression events graph that has, no, because we need to make this graph into the analog of the spatial hypergraph, we have to project it onto atoms, right?
What if projected onto atoms?
Well, I mean, in other words, if we want to draw the effect of this light cone, not on these events, but on a spatial hypergraph, we have to see what those events, what consequence those events have for the spatial hypergraph.
Right.
And I think what we did up here right, effective spatial ball is looking at the causal graph, right? Is looking at, that's the intersection of the light cone with this, correct?
Yeah.
So we can either look at this or we can look at the causal edge, how the causal edge intersects. There are two views of it. We can either look at this and how this grows and I mean, I wonder what happens if we use a completely different. I mean, what happens if we use one of these more like Turing machine type things? That let's just see what happens here. So this is the effective spatial ball. Which did I have to use? No, this is okay. This is going to work for a hypergraph, right?
I think so. Well, it probably just tell you where the head has been.
Right. Well, okay. Okay, so let's see. Let's pick a rule that is let's pick this crazy rule here. Okay, so what we want to do here, say 1,000 here. I bet it's not going to be enough to say 2 for the spatial reconstruction there. I bet we have to have a spatial reconstruction that has visited the whole of the universe.
Yeah. Oh, I think the last layer only has one event, so it.
But I think I'm going backwards here in the spatial reconstruction thing.
But spatial reconstruction only shows you the last generation.
Oh. So how can we deal with this?
Well, what do you want to do? If you have spatial reconstruction which shows you more than the last generation, it's just a causal graph, more or less. You can, let's see. Well, the events always depend on one another. So there are multiple expressions at the last generation, but only one event.
Yeah.
So if you use expressions common past graph, you can do it then.
Okay. I clicked to copy as not self-contained.
I think it's.
Sorry, go ahead.
Isn't it self-contained? What's not self-contained?
Oh, maybe it is. I'm sorry.
It's just in a weird order.
Yeah, all right. You're right. Okay. So here, well, I don't know whether this is going to help us. I mean, we can certainly look at this one. Okay, whatever that means. Okay, great. I don't know what that means though. But what are you saying? You're saying, what are you saying here?
What?
No, how to compute this. I mean, so in other words, what we want to do is we want to find an example where we can see the comparison between this thing here growing out on these edges, okay? See, the question is, can we start with a geodesic ball on every element of this light cone thing? No, we cannot do that. We have to start in the center of the light cone. Oh, boy. Because we don't know which time-light curve corresponds to the center.
Right. Still think we need stable structures, because then we could just compare the light travel from one to another. And
yes, I agree. I think we have to get further with the model to be able to do this.
yeah.
But I think qualitatively, what we think is going to happen is that if you can kind of predict the fluctuation of space, I reckon you can get an advantage. Now the question is, can you get an infinite advantage or just a finite advantage? See what I'm saying?
Yeah.
And also, see, I think in our model, the closed time-like curves thing is not a thing. You just can't, you know, what is the condition for the causal graph to not have closed time-like edges, closed time curves? It's basically the state.
Right now in the implementation of Wolfram model, it can't. In order to do it, you need to identify expressions which are time-like separated.
Right.
And it's not clear what if one was to do it, how one should do it, and so on.
Current setup, there cannot be CTCs because we don't do isomorphism between time-like separated expressions.
Well, the global multivariate system does it by just doing isomorphism, but I think it's a lot more subtle than that. Because how you actually do isomorphism and identify expressions, that's a difficult question.
Yeah, right. And right. But I don't think this phenomenon, in other words, we're basically violating relativity by, you know, a subspace demon can absolutely violate relativity. Because a subspace demon violates the computational irreducibility condition necessary to derive relativity.
Why do you need irreducibility for relativity?
Because you certainly need it for general relativity. Do you need it for special relativity? Because you need to be able to replace. I think you need it because otherwise you've got all kinds of discrete junk there. I mean, it's the thing that allows you to take a continuum limit.
Well, you need it to be random.
Why do you need it to be random?
Which I guess kind of
Why do you,
implies irreducibility.
yeah, why do you need it to be random? What do you need to be random to get relativity? I'm not actually sure.
Well, space, because
Why?
well, it's either random or it looks random. Because if you have a grid which is not random, it wouldn't be Lorentz invariant. I mean, it wouldn't even be isotropic.
Right.
I mean, there are some special grids which are isotropic.
Sure.
Look very random.
Right. But, basically need to get isotropy and arbitrary boosts working. But that's not because you need it. Let's see, that's not because you need it for the causal invariance side of it. You need it for some other reason. Why do you need it? Why do you need it? And by the way, I mean, what will be the effect of a subspace demon? Maybe it should be called a space demon. I don't think it needs the subspace. Okay, so how does a space demon violate Lorentz invariance? And what does it actually look like? I think a gas demon will undoubtedly violate Galilean invariance for whatever the same reasons. But what does it actually look like? So the space demon is picking particular causal edges. I see. Look, what's going to happen is, yes. The space demon is not frame independent. Because the edges it picks are not frame independent. By the way, the reason you need computational irreducibility is to be able to take the limit for an arbitrary frame somehow. Let's think about that. Do you understand that? Why you need that? Well, it's getting late. We've made some progress here.
Yeah.
And we got a few to-dos for these different types of graphs. And we got a new
I have
graph
a
color.
lot of to-dos.
Okay, we've got a new graph color. That's very exciting. I haven't had a new one of those in a while.
Yeah, between yesterday and today, I have 13 to-dos.
Yeah, well,
I put good first issue and help wanted on some of them, but I don't know if it attracts anyone.
well, let's see.
We need more software engineers in the project.
Yes, and we should be able to find them.
They don't even need to know any physics.
Well, you're the one to recruit those people.
Well, recruitment is not really my skill. I don't even know where to start.
Well, you should bring this up in the group meeting. You should bring this up. You should send out mail to the internal list, and see what we can do. I mean, I think